In mathematics, the dot product, or scalar product, is an algebraic operation that takes two equal-length sequences of numbers and returns a single number. This operation can be defined either algebraically or geometrically. Algebraically, it is the sum of the products of the corresponding entries of the two sequences of numbers. Geometrically, it is the product of the Euclidean magnitudes of the two vectors and the cosine of the angle between them. The name dot product is derived from the center dot AAA that is often used to designate this operation. The alternative name scalar product emphasizes the scalar nature of the result. In three-dimensional space, the dot product contrasts with a cross product of two vectors, which produces a pseudovector as the result. The dot product is directly related to the cosine of the angle between two vectors in Euclidean space of any number of dimensions. Definition: the dot product is often defined in one of two ways, algebraically or geometrically. The geometric definition is based on the notions of angle and distance. The equivalence of these two definitions relies on having a Cartesian coordinate system for Euclidean space. In modern presentations of Euclidean geometry, the points of space are defined in terms of their Cartesian coordinates, and Euclidean space itself is commonly identified with a real coordinate space Rn. In such a presentation, the notions of length and angles are not primitive. They are defined by means of the dot product. The length of a vector is defined as the square root of the dot product of the vector by itself, and the cosine of the angle of two vectors of length 1 is defined as their dot product. So the equivalence of the two definitions of the dot product is a part of the equivalence of the classical and the modern formulations of Euclidean geometry. Algebraic definition: the dot product of two vectors equals a1, a2, and b equals b1, b2. Bn is defined as where I denotes summation notation and n is the dimension of the vector space. For instance, in three-dimensional space, the dot product of vectors 1, 3, a 5, and 4, a 2, a 1, is. Geometric definition: in Euclidean space, a Euclidean vector is a geometrical object that possesses both a magnitude and a direction. A vector can be pictured as an arrow. Its magnitude is its length, and its direction is the direction the arrow points. The magnitude of a vector A is denoted by the dot product of two Euclidean vectors A and B is defined by whereas the angle between A and B. In particular, if A and B are orthogonal, then the angle between them is 90 degrees and at the other extreme, if they are codirectional, then the angle between them is 0 degrees and. This implies that the dot product of a vector A by itself is, which gives the formula for the Euclidean length of the vector. Scalar projection and first properties. The scalar projection of a Euclidean vector A in the direction of a Euclidean vector B is given by whereas the angle between A and B. In terms of the geometric definition of the dot product, this can be rewritten. Where is the unit vector in the direction of B? The dot product is thus characterized geometrically by the dot product, defined in this manner, is homogeneous under scaling in each variable, meaning that for any scalar I plus or minus. It also satisfies a distributive law, meaning that these properties may be summarized by saying that the dot product is a bilinear form. Moreover, this bilinear form is positive definite, which means that it is never negative and is zero if and only if equivalence of the definitions: if E1, n are the standard basis vectors in Rn, then we may write the vectors are an orthonormal basis, which means that they have unit length and are at right angles to each other. Hence, since these vectors have unit length, and since they form right angles with each other, if E are permal Aj. Now applying the distributivity of the geometric version of the dot product gives, which is precisely the algebraic definition of the dot product. So the dot product equals the dot product. Properties: the dot product fulfills the following properties if A, B, and C are real vectors and R is a scalar. Commutative, which follows from the definition. Distributive over vector addition. Bilinear. Scalar multiplication. Orthogonal, Two non-zero vectors A and B are orthogonal if and only if AB equals 0. No cancellation, unlike multiplication of ordinary numbers, where if AB equals AC, then B always equals C unless A is 0. The dot product does not obey the cancellation law. If AAB equals AAC and AA permel 0, then we can write AA equals 0 by the distributive law. The result above says this just means that A is perpendicular to, which still allows a permel 0, and therefore BA permel C. Derivative: if A and B are functions, then the derivative of AAB is or euro squared AB plus AA bar euro squared. Application to the cosine law. Given two vectors A and B separated by angle I, they form a triangle with a third side C equals AAB. The dot product of this with itself is, which is the law of cosines. Triple product expansion. This is an identity involving the dot and cross products. It is written as, which is easier to remember as BAC minus CAB, keeping in mind which vectors are dotted together. This formula finds application in simplifying vector calculations in physics. In physics, vector magnitude is a scalar in the physical sense, that is a physical quantity independent of the coordinate system, expressed as the product of a numerical value and a physical unit, not just a number. The dot product is also a scalar in this sense, given by the formula, independent of the coordinate system. Examples include, mechanical work is the dot product of force and displacement vectors. Magnetic flux is the dot product of the magnetic field and the area vectors. Generalizations, complex vectors, for vectors with complex entries, using the given definition of the dot product would lead to quite different properties. For instance, the dot product of a vector with itself would be an arbitrary complex number, and could be 0 without the vector being the zero vector. This in turn would have consequences for notions like length and angle. Properties such as the positive definite norm can be salvaged at the cost of giving up the symmetric and bilinear properties of the scalar product, through the alternative definition. Where B is the complex conjugate of B, then the scalar product of any vector with itself is a non-negative real number, and it is non-zero except for the zero vector. However, this scalar product is thus sesquilinear rather than bilinear, it is conjugate linear and not linear in B, and the scalar product is not symmetric, since the angle between two complex vectors is then given by. This type of scalar product is nevertheless useful, and leads to the notions of Hermitian form and of general inner product spaces. Inner product. The inner product generalizes the dot product to abstract vector spaces over a field of scalars, being either the field of real numbers or the field of complex numbers. It is usually denoted by the inner product of two vectors over the field of complex numbers is, in general, a complex number, and is sesquilinear instead of bilinear. An inner product space is a normed vector space, and the inner product of a vector with itself is real and positive definite. Functions. The dot product is defined for vectors that have a finite number of entries. Thus these vectors can be regarded as discrete functions. A length n vector U is, then, a function with domain KAAA 1 pound of permel currency Ka permel currency n, and E is a notation for the image of I by the function vector U. This notion can be generalized to continuous functions, just as the inner product on vectors uses a sum over corresponding components. The inner product on functions is defined as an integral over some interval AA permel currency x A permel currency B. Generalized further to complex functions I, x, and I, x, by analogy with the complex inner product above, gives. Weight function. Inner products can have a weight function, that is a function which weight each term of the inner product with a value. Dyadics and matrices. Matrices have the Frobenius inner product, which is analogous to the vector inner product. It is defined as the sum of the products of the corresponding components of two matrices A and B having the same size. Dyadics have a dot product and double dot product defined on them. See dyadics for their definitions. Tensors. The inner product between a tensor of order n and a tensor of order m is a tensor of order n plus ma2. See tensor contraction for details. See also, Cauchy-Schwarz inequality, cross product, matrix multiplication, references. External links, Haswinkel, Michiel, ed., Inner Product, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Wallerstein, Eric W., Dot Product, MathWorld. Explanation of dot product including with complex vectors, Dot Product by Bruce Torrance, Wolfram Demonstrations Project, 2007.